Hi dear students, so in this lecture video I am going to tell you about the what the torsion of shaft. What do you mean by torsion of shaft? Okay, what is the importance of torsion and what is the definition of torsion and finite element formulation, okay, of that given twisted that is the torsion shaft. Okay, so finite element formulation is nothing but you have to derive the element stiffness matrix for torsion. Okay, how you derive the element stiffness matrix for 1D bar element in module 1? Similar way we are going to derive a equation, that is what the torsion stiffness matrix, that is K is equal to, okay, what is the stiffness of the torsion. Okay, along with that, so also we are going to discuss about this Euler-Bernoulli beam. Okay, so that's what this syllabus. Okay, coming to the last end topic, so torsion of shaft. Okay, that is today we are going to we are going to explain now this finite element formulation of the given shaft. Okay, so here before starting that derivation, that is finite element formulation, let me understand what you mean by torque. Okay, normal definition, if you tell torque, nothing but what? Twisting moment, that is force into distance if you take while solving the problem. Okay, so torque is nothing but what? The product of turning forces and the corresponding distance is known as a torque. Okay, that is the distance is one between the point of the application force and the axial of the shaft, that is force into distance we are going to consider while calculating the torque. Okay, if you apply a torque, if you apply twisting moment or any of the given shaft, okay, it will causes what? It will distribute the stresses over the entire cross section of the area of the shaft. Okay, and along with that it will induce or it will causes the moment bending, stress, strain, all those things. Okay, so this is the definition of torsion. Okay, so torsion is nothing but force into distance. Okay, that is the twisting moment takes place in a particular shaft if you apply torque means. Okay, so torque, if you apply the torque, the twisting moment takes place. Okay, the best example for this torque moment is, that is here the twisting is a simple piece of a blackboard. Okay, this is an example for this torque element. Okay, so twisting a simple piece of a blackboard chalk between the one finger until it snaps awkward, that is with respect to that chalk. Okay, so is a best example for this torsion. Okay, now so just in this slide just you understand that torsion, what torsion means, what? Okay, there is a twisting movement in a given particular shaft. Okay, because of this twisting moment, okay, we are going to induce, it will causes the what? The stress, strain. Okay, so that will causes in the particular shaft of the whole area of the given shaft. Okay, so look at this torsion. Okay, so this is the formula for torsion. Okay, so tau shear stress is equal to R and T is by J, which is equal to G theta by L. Okay, where for this is for the solid element we are going to use. Okay, J is equal to pi raised to the power of 4 32 for solid rod. Okay, so this formula I am going to use while solving the problem. Okay, so look, by depending upon the given problem, solid cylindrical structure or hollow cylindrical structure and solid cylindrical structure. Okay, so for the solid structure we are going to use to calculate J is equal to pi d to the power of 4 32. Okay, so look at this here, that there are two shafts will be there here. Okay, solid shaft. Okay, solid shaft, this is a shaft is there. Okay, so J here for the solid shaft we are going to use same formula here what I mentioned here, that is J is equal to pi r to the power of 4 by 2 in terms of their given radius means, suppose they in terms of the given diameter means we are going to use pi d to the power of 4 32. Okay, whereas in the hollow space, okay, that is the hollow shaft, we are going to use we are going to subtracting the larger diameter minus smaller diameter, that is pi by 32 d to the power of 4 minus d square. Okay, this formula I have to remember while solving the problem for solid shaft and hollow shaft. Okay, so this is the torsion. Okay, look at this is a beam element. Okay, so when if you apply the twisting moment, okay, so opposite here we are going to get, it will induce what? The stress and strain in the particular shaft. Okay, entire roll. Okay, so look at this angle will produce here theta. Okay, so here where notations what? Here the notation shear stress is equal to what? This tau is equal to shear stress and measured in megapascal. Okay, R is the radius, tau is the torque. Okay, G is equal to polar second moment of area. Okay, so G is the modulus of rigidity and theta is the angle of twisting moment takes place when if you apply the torsion on this element, and L is the length of an element. Okay, so from this slide you have to remember only these two formula, that is for the solid shaft, for the solid shaft you are going to use this formula, and for the hollow shaft you are going to use this formula. Okay, so I am going to write direct. Okay, so in the while solving the problem you have to remember this. Okay, and this is also very important to derive the element stiffness matrix for torsion element. Okay, you remember this element. Okay, this formula. Okay, then what is the application of this torsion? Okay, normally the torsion spring is commonly used in clothespin and clipboard. Okay, swing down tailgates and gear gauge doors. Okay, so other application apart from this mechanical, it include the hinges. Okay, counterbalance and lever terms. Okay, these are some of the application we are going to use in the torsion. Okay, so let me, what do you mean by shaft? Okay, so many students will ask what do you mean by shaft. Okay, shaft is nothing but what is the supporting element in the given vehicle, that is what? It is a long piece of a metal, usually a circular in cross section area will be there in an engine or a machine that turns the transmit power. Okay, that is moment takes place with the help of this shaft. Okay, to produce electricity or whatever it will work work the it will, with the help of this shaft, we are going to convert, we are going to use the mechanical, we are going to get the mechanical energy. Okay, these are used for transmitting the rotary motion and the torque from one point to the another point. Okay, so shaft has very important role in an automobile vehicles. Okay, so from this slide what you understand that, so torsion means what? Torsion nothing but the that is what force into distance, the twisting movement takes place because of torsion on the particular shaft. What it will causes the deformation and stresses strain, okay, and the entire length of the body. Okay, so that you have to remember. And for hollow cylindrical structure, where what is the formula, and solid cylindrical structure, what is the formula, you have to remember. Okay, so now the next question is to derive the element stiffness matrix for this what the torsion element. Okay, so it is also called as finite element formulation. Okay, so in examination many times they are asking explain a finite element formulation for torsion. Okay, so you have to derive the element stiffness matrix for this torsion. Okay, so here before solving the torsion, it is similar what before solving this torsion element structure, so the stiffness matrix and the load vector can be derived by replacing the same, that is the axial rigidity, in place of what we are going to derive in the 1D dimensional element. Okay, so that is element stiffness matrix for 1D element, we have to replace this A and D by using this torsion rigidity. Okay, G and J. Okay, and the distributed load axial force by the is replaced by what? The distributed torque. Okay, the axial force replaced by torque. Okay, the concentrated axial force is replaced by concentrated torque. Okay, so distributed torque, concentrated torque, AE replaced by G, that is rigidity JG. Okay, so G, J you have to replace. Okay, if you do this, you are going to get the element stiffness matrix for this what torsion. Okay, so it is similar to the 1D bar element. If you perfect that element stiffness matrix for 1D bar element, then it is very easy to derive. Okay, so look at this in examination, they may ask you like explain the finite element formulation or derive stiffness matrix for torsion. It is not called stiffness matrix, but we are going to call sometime. Okay, so here the finite element formulation, this is very important question, they may ask you around 6 to 8 marks. Okay, look at this, consider a 1D two noded one dimensional two noded torsional elements. So this is a one dimensional torsion element. Okay, as shown in the below figure. Let T1 and T2 be the torque. So let here where we are going to displacement, we are going to consider the displacement. Okay, but here we are going to consider as torque. Okay, so let T1 and T2 be the torque at node number 1, at node number 2. Okay, whereas the angle of twist, okay, once if you twist moment takes place, here the angle of twisting moment at node number 1 is taken as what? The angle of rotation, those are called as angle of rotation. At node number 1 is phi 1, at node number 2 is phi 2. Okay, respectively. Okay, so here T1 phi 1, in beam element what we are going to take? V1 theta 1. In the truss problem what we are going to take? U1 V1. Okay, so that you have to remember all those values. Okay, so consider a one dimensional torsion element. So T1 and T2 be the displacement at node number 1 and at node number 2, and phi 1 and phi 2 are the angle of rotation at node number 1 and 2. Okay, so this is the length of this torsion element. Okay, so let us consider from this axis. Okay, let us assume this we need to calculate. Okay, from here to, so here distance is x1, from this point to this point. Okay, this is what the x2. Okay, what is the this length they given? Okay, so the total length from this to this is equal to what? X2 minus, you have to calculate this x1 which will use this. Okay, so remember this is about the diagram. Okay, so angle of twist or angle of rotation, that is phi of x at any point. Okay, within the element in a linear polynomial function we are going to take an as this phi of x is equal to a0 plus a1x. Okay, since it is a 1D bar element, so up to we have to take, so a0 is equal to a1 plus ax. Okay, now apply the boundary condition at node number 1 at node number 2. Okay, so when x is equal to x1, phi is equal to phi 1, so substitute in this equation you are going to get phi 1 is equal to a0 plus a1 x1. Okay, at node number 2, x is equal to x2, phi is equal to phi 2, substituted in this equation you are going to get phi is equal to a0 plus a1 x2. Okay, so now you subtract from this to this, that is phi 1 minus phi 2. Okay, so here a0 going to get cancelled, so remaining is a1 x1 plus this is what remaining what a1 x1 a1 x1. Okay, so here a2 a1 x1. Okay, so now what you are going to get here, this is a a1. Okay, this is not a2, this is a1. Okay, so phi 1, so get the a1 is equal to what? This is the a1. Okay, so this is not a a2, I am telling. Okay, this is a1. If you simplify, a1 is equal to this goes this direct, this comes this side, so a1 is equal to phi minus phi 1 whole divided by x2 minus x1. Okay, so this is the a0 value. Again we have to substitute this a0 value in any one of the equation. Okay, that is in this equation, so you are going to get a0 is equal to phi of phi 1 x2 minus phi 2 x1 whole divided by x2 minus x1. Okay, so after getting this a0 and a1 value, so I already told number of times, so this a0 and a0 value are the generalized coordinate system that we need to find out by applying the boundary condition. Okay, after getting the a0 and a1 value, substitute in this equation. Okay, so from the equation number this, okay, so substitute this a0 and a1 value in this equation, you are going to get this equation. Okay, that is phi is equal to phi 1 x2 minus phi 2 x1 whole divided by x2 minus x1 plus x2 minus x1 whole divided by phi 2 minus phi 1 into x. Okay, next on simplification, so we already we know that this what x2 minus x1 nothing but what L. Okay, so this the length of this element x2 minus x1 is gives the L. Okay, so same again just to modify that one. Okay, so phi is equal to x minus x whole divided by L phi 1 plus x minus x1 whole L by phi 2. Okay, so from this, so it is similar, this equation can be modified as phi is equal to this, let us consider this is what the n1 and this is called as n2. Okay, so where n1 and n2, we know that n1 and n2 are called the shape function. Okay, so which n1 value is this and n2 value is this. Okay, therefore n1 is equal to the what x2 minus x1 whole divided by L and n2 is equal to x minus x1 whole divided by length of element or the shape. These are the two are the shape functions. Okay, so it is similar to the analysis of bar. Okay, that is a stress strain relationship for the torsional circular shaft can be expressed as what stress is equal to, so this what the strain into this stress is equal to Young modulus into strain. Okay, so where stress is equal to what, we know the in the stress formula for whereas in the normal bar element the stress is equal to what, stress is equal to what in the previous case. Okay, so that is stress is equal to Young modulus into strain, whereas here in this case we are going to take the just to replace torque into area. Okay, stress is equal to force per unit area we are going to take there. Here in place of axial force we are going to replace as this torque. Okay, so normal definition for stress is equal to force per unit area, so wherever force is there we are going to use here torque. Okay, torque by area. Okay, where this D stands for this stress stands for this T by A. Okay, so material property D is equal to what, we have this, we know this material property Gj by area. Okay, so that is in place of there you are going to take EI, that is AE. Okay, AE, that is what there AE you are going to take, so AE replaced by G comma J. Okay, so now strain is equal to what, that is strain is equal to change in deformation. Okay, that is dy by dx. Okay, so which is equal to what, so B, so you substitute this formula. Okay, B matrix of B into QB. Okay, so where B stands for what, the stress element will be there. Okay, stress is equal to 1 by L minus 1 1, so phi 1 phi 2. Okay, so where J and G are stands for the J stands for the polar moment of inertia and G stands for what, modulus of rigidity, and A stands for the area of cross section. Okay, so now after calculating this we know that from the concept of the what potential energy function, so potential energy function is equal to what, the sum of strain energy plus work potential. Okay, strain energy nothing but what, the stored energy, work potential it is due to external force. Okay, so the strain energy for the given torsion beam is, we have this formula. Okay, so that is half of integration of stress okay, strain into dV, and work potential it is due to external force. Okay, displacement and force. Okay, so after simplification this we are going to get strain energy is equal to half of integration QV T, just you write here. Okay, so where K, so stress is equal to KE and QE. Okay, so where K nothing but the element stiffness matrix which is given by this formula. Okay, on simplification this, okay, similar to the what you are simplified in the one dimensional element, so you are going to get this equation. Okay, stiffness matrix where K is equal to Gj by Le 1 minus 1 minus 1 1. Okay, so where, okay, so again the equilibrium, according to the equilibrium condition, what K what K U into F. Okay, so here K value is this, that is Gj by Le 1 minus 1 minus 1. These are the displacement. Okay, rotation displacement phi 1 and phi 2. These are the torque. Okay, so this expression we are going to call as element stiffness matrix for torch element. Okay, so this derivation is very important for the point of examination in part 2 in module 3. Okay, you have to remember this derivation. Okay, so where G stands for the modulus of rigidity, J stands for the polar moment. Okay, second polar moment, and L stands for the what, the length of element, and phi 1 and phi 2 are the angle of rotation. Okay, that is the angular displacement, and T1 and T2 stands for what, the torque. Okay, so many times they are in the examination they are considering as temperature. Okay, not it is temperature, it is a torque applied on the given element at node number 1, at node number 2, at node number 1, at node number 2. Okay, so this formula you have to remember. Okay, it is in place of AE by LE, here JG comma. Okay, so G comma J, you have to remember this. Okay, so this expression you are going to call as element stiffness matrix for torsion or finite element formulation for this torsion. Okay, so this is what the derivation. Okay, coming to the Euler-Bernoulli beam. Okay, so this is not for, okay, so just you understand that Euler-Bernoulli beam nothing but what. Okay, so let us assume this is a what, this is a beam. Okay, okay, a plane section normal to the beam axis remains plane. Okay, So before bending this beam, so the normal, that neutral axis is, if you consider a 90 degree, so that is normal to the this axis. Okay, after bending also it will become what the normal only we are going to consider. Okay, that is the main concept behind this Euler-Bernoulli beam. Okay, so plane section normal to the beam axis remain plane, and normal to the axis after deformation okay also is a plane only. Okay, that is the difference. Okay, suppose how you are going to understand means, suppose before bending, if you consider from this to this axis, okay, it will become normal only. Okay, after bending also this, the distance from this point to this point is also become normal only. Okay, that is what says the Euler-Bernoulli thing. Okay, so this is what the bending, this is the neutral axis. Okay, this is one end is fixed, this is one end is fixed. Okay, so look at here, I told here, I mentioned here, all the beam section are straight and perpendicular to the neutral axis only. Okay, before bending, after bending, that is main important in this Euler-Bernoulli beam theory. Okay, so the Euler-Bernoulli beam equation is widely normally used in the engineering, especially in civil and mechanical, to determine the strength or that is the deflection of a beam under the bending moment. Okay, so both bending moment and the shear force caused by the stresses in the beam element. Okay, so these the main application of this Euler-Bernoulli beam theory we are going to use to calculate what the stresses present in the given okay, that is to calculate the strength present in the given beam in a civil and mechanical problems. Okay, so just to remember that Euler-Bernoulli beam nothing but before bending, after bending. Okay, the all the beam sections straight and perpendicular to the neutral axis only, that we have to remember this. Okay, so this is about the Euler-Bernoulli beam. Okay, so now this is about what the derivation for torsion of element and what the Euler-Bernoulli beam. Okay, I hope you understand this derivation. Okay, so derivation is very important for the point of examination in second half of the module 3 chapter. Okay, so I hope you understand this. Okay, thank you.